Welcome to the 10th lecture. In which we are going to learn more about the functionally graded materials. Let us quickly highlight what we discussed in the set of last lectures, that we are looking for advanced structural systems which are designed to be form dominant. We are also looking for materials which support this system for its functional and structural requirements. Structural requirements refer to the mechanical properties such as yield strength, Young's modulus, Poisson's ratio, fatigue strength, fracture resistance, which are generally and possibly very good as far as different steel grades are concerned. There are no issues about it. When you come to the functional aspects of steel, especially under the influence of environment, to be very particular in marine environment, steel undergoes corrosion, and that is one of the disastrous requirements which is not agreed upon by any engineer in practice for marine systems. So, we are looking forward for a material which is having similar strength to that of steel, but possesses better corrosion resistance. So, we are looking for a functional requirement of the material. So, advanced steel design is dealing with two aspects of the design procedures. One is the geometric centric design, where the structural assembly takes care of the load acting upon the structure. Apart from the advanced design procedures such as plastic design, etc. In addition, we are also looking for a material which is compatible with this large displacement structural systems. What does it mean? The material should possess enough ductility. To adopt plastic design, the elastoplastic domain of the material should be very dominant. To have good toughness, the area of the stress strain curve should be large enough. The material should exhibit ductility, etc. Apart from possessing these advantageous properties, we will also choose a specific requirement, let us say corrosion resistance, which is indefinitely required in marine environment. So, we did a recent research at IIT Madras with assistance with Professor Murugayan in Department of Metallurgy and Material Sciences. We came out with a fabrication of a new novel material which is functionally graded of different constituents to have corrosion resistance and strength at par with steel. So, in this lecture we are going to talk about that particular recent innovation on FGM, which is yet to be applied to marine systems, but still it is in the research stage, and I believe you will love to know more information about this kind of research advancements in structural design as far as steel is concerned. So, in FGM again, steel is an important ingredient, but the corrosion resistance is improved by combining or alloying this with another metal. That is what we have tried to do it. Okay? Let us do this and see how do we proceed with this further. As we said in the last lecture, FGM is actually grading two or more metal components or metal to fulfill a particular functional requirement. So friends, at this moment we are taking the functional requirement as corrosion resistance. Okay. There can be any such functional requirements, let us say low thermal conductivity, high temperature performance, excellent fatigue characteristics. You can dictate, you can choose any specific functional requirement and modify the characteristics of steel by altering the ingredient metals to form a functionally graded material. So, as I said, there are many manufacturing processes which are available in the literature to fabricate a functionally graded material, out of which wire arc additive manufacturing is one of the prominent method, which is compatible manufacturing procedure, which enables the metallurgical components of the materials to be user defined. So, it permits user defined metallurgical composition of materials to be graded. Okay. So, it is user friendly. So, it does it. So, in VAM, stepwise addition is done. We have already said continuous and stepwise are two different methods of FGM manufacturing. In VAM, stepwise addition is generally carried out. Okay. The manufacturing process is controlled in a digital mode. So, the manufacturing process is digitally controlled. Whereas, materials are chosen as per the functional requirements. Friends, usually 2 or 3 materials are graded, okay, not more than that. You can have more, but the complexity of manufacturing will be very large. So, usually 2 or 3 materials are graded to get a FGM product. So, in VAM what we do, these chosen materials are interchanged or let us say deposited in the form of wires. So, VAM has got a great advantage over the powder bed process in terms of deposition rate, equipment cost, cost of the raw material, etc. So, this has got an edge over this particular process of manufacturing, and VAM is considered to be advantageous compared to this. Okay. In the VAM process, the raw material, or I should say the ingredient metals, are added in the form of wires. So, I should say the metallic powder is replaced as wires, okay, in metallic powder bed process. The metal powder are actually added. In this case, the raw material is added in the form of wires. And for manufacturing, electric arc is used as the heat source. Therefore, friends, VAM is considered to be economically viable and it is capable of manufacturing large size members. It is also capable of manufacturing any shape, including circular, because circular is considered to be one of the most difficult fabrication process. Furthermore, it has got a minimum wastage of materials. So, I should say this process is highly economical compared to the conventional processes used in manufacturing alloys or composites. Okay. High pulse current rate is applied to form an electric arc. And that is remaining as a heat source for the problem. Now, let us talk about a specific application of FGM for marine riser. So, let us say we take a member for our consideration. The member of our choice is the marine riser. Now, the question is, for the knowledge of other people listening to this course who are not offshore engineers, let us quickly explain what is a riser. Let us say if this is my offshore platform which is having multi-tier deck, which has got the crane facility, which has got the top side details in terms of drilling platform, drilling derrick, etc., and a helipad. Let us say the platform is constructed and resting on the seabed by a template arrangement structural system, and this becomes my water level. Let us say from the drilling head, a pipeline is driven to the seabed, which is now going to explore the oil and it is going to be carried up through this pipeline and then it is processed or stored on the top side. Since the oil is travelling against gravity, this component is called as a riser, and since it is used for marine application, so it is a marine riser. So, marine riser is actually a circular pipe or a cylindrical tube which is essentially used to explore, suck oil or gas from the seabed to the top side. Okay. So, our application member is a marine riser. You can see here the marine riser is completely embedded in sea water, which is corrosive in nature, and in addition to that, the oil and gas which is passing through this riser is of a very high pressure and high temperature. So, now we are looking for a member which is located in the corrosive environment. The member should sustain high pressure. The member should also sustain high temperature. So, we are looking for a material which caters to these functional requirements. Okay. If you ask me a question, what is the general material being used currently in the industry? Because oil and gas exploration is not today's job. The first oil well was drilled in the United States in the year 1912, 100 years back. Okay. So, this process is there for the past 100 years. So, people must have been using some material for marine risers. Okay. We state that they are corrosive in nature, but people have been using them. So, what is that material being conventionally used so far is X52 grade steel, which is the marine steel. I will show you the mechanical properties of this steel slightly in a minute later in the next slide. Okay. It is a conventional steel being used. Now, we want to replace this steel with a new material which is functionally graded. So, to improve the performance of corrosion resistance, we are looking for alloying the duplex stainless steel with carbon manganese steel. So, friends, these ingredients, these metallurgical constituents are chosen based on specific functional requirements. Okay. The functional requirement what I have is, of course, the strength. There is no compromise on strength. We are also looking for additionally a corrosion resistance, right. So, we can choose these two materials. If you ask me a question, do only these two materials available which are corrosion resistant? There are many. Titanium, there are many material available. For example, we are demonstrating an FGM fabricated in our lab with these two materials. You may ask me why duplex stainless steel? That is a common material being currently used as a single material for risers. So, we want to add that to carbon manganese steel and see whether corrosion resistance can be improved. Okay, that is the question here, that is the argument. Okay. Having said this, if you look at the properties of duplex stainless steel, it has very high corrosion resistance, towards hydrogen sulfide gas, carbon dioxide gas and acidic environment. It is also capable of resisting cracks arising from stress concentration. Okay. Now, we want to add this material with carbon manganese steel, which is X52. So, X52 is a carbon manganese steel which is currently used as marine steel in risers. So, we want to add this the duplex stainless steel and see what happens. Okay. Let us quickly see the stress strain curve of materials what we are discussing now. Before we go that, let us see the material what we are choosing and what is the code compliance of this, because we already said the choice of the material also depends on whether the code accepts it or not. So, duplex stainless steel is anyway recommended as 22 CR, ER 2209, which is recommended by DNVGL RP F112. Carbon manganese steel is also recommended for marine application, which is ER 70S6, which is recommended by DNV OS F101. So, friends, one can easily get convinced that these two ingredient steel are not new, recommended for marine environment. Already existing codes permit use of this material for marine environment. So, code compliance is satisfied. So, one can really go for alloying these materials and see what happens. Okay. Now, let us look into the stress strain curve of carbon manganese steel. The one what you see on the screen is the stress strain curve of carbon manganese steel. Okay. So, the carbon manganese steel does not have a pronounced yield point. So, to obtain this, one can easily find out the 0.2% proof stress value and get the yield strength. One can also see it has got enough ductility. Okay. Carbon manganese steel possesses enough ductility, right, because the ductility ratio is significantly larger for this steel. Okay. So, this is the stress strain curve for carbon manganese steel, which is going to be the ingredient for my FGM. So, what is that element we are looking at, how we are going to compose it? Let us see that here now. I am looking for a marine riser which is circular in cross section, which should be now functionally graded, correct? With two materials, one is duplex stainless steel, other is carbon manganese steel. Okay, we are going to do this. Let us see how we are going to show the cross section. A typical cross section of the proposed riser is now shown on the screen. So, the cost of duplex stainless steel is phenomenally high compared to carbon manganese steel. Friends, it is because of this reason duplex stainless steel as such as a single material is not being used as a riser. Okay, the cost will be phenomenally high. Carbon manganese steel is cheaper compared to duplex stainless steel. Therefore, what we propose is only a small portion will be duplex stainless steel and the majority will be carbon manganese steel. So, economically the proposed new material will not be very expensive in comparison to the conventional carbon manganese steel, because you are adding only one layer of duplex stainless steel. But remember, it is not a coating, it is not a composite, it is not a layering material, it is fabricated as a single material. That is the beauty here. Okay. So, the functionally graded riser now has got two material where the inner portion will be susceptible to corrosion because of HPHT conditions, okay, and the carbon manganese steel is located outside, as you see in the screen here. Okay. Having said this, that we now have the cross section, we now have the material, let us see what would be the thickness we are proposing. Let us say what is the material and what is the thickness we are proposing. Okay. So, the material we are saying is duplex stainless steel, which is 22 Cr 2209, which is only for 3 millimeters, whereas the carbon manganese steel, which is qualifying ER 70S6 grade, is about 14.47 millimeters. So, the total thickness of the riser is 17.47 millimeters, out of which 3 millimeter is duplex stainless steel and remaining is carbon manganese. So, now one will be curious to know, how do we get this thickness of the riser? That is a very interesting question, friends. We have taken a live example of a riser present in Auger TLP, tension leg platform, in the Gulf of Mexico, and we have adopted the same cross sectional dimension of the riser for the analysis. The marine riser present in the Auger TLP is of thickness 17.47. Please note, the existing riser present in Auger TLP does not contain duplex stainless steel. It is a single layer material, it is not FGM. So, we are now improving the corrosion resistance of that material by adding stainless steel of a marginal thickness, okay, without compromising the strength. Let us see what happens to this combination, right. So, we are looking for a thickness of this order. Now, we have the cross sectional dimensions ready, we have the material composition ready, we have the thickness to be done ready, we also have the manufacturing process, which is also finalized. I am going to use wire arc additive manufacturing, where I am going to feed the carbon manganese steel and duplex stainless steel in the form of wires. I am going to manufacture this, okay, in layers. Having said this, let us see what the code advises for the desired wall thickness of risers. The desired wall thickness of marine risers should take care of the corrosion allowance. So, the minimum thickness is the internal pressure, the nominal diameter divided by twice of eta h sigma y plus thickness meant for corrosion, equation 1, whereas Pi is internal pressure, d nominal is the nominal diameter of the member of the riser, eta h is a usage factor, which is a factor used in the design. Usually this value is taken as 0.6, and the corrosion allowance given is about 6.265 millimeters. As per international practice, the minimum corrosion allowance given is 3 millimeters if you provide carbon manganese steel. So, this is not TC, this is the minimum. Okay. So, you provide T minimum for corrosion as 3 millimeter, then work out for the given pressure and diameter, and this work out T minimum, that comes to be 6.265 millimeters. Okay. So, friends, please note, along the inner surface of the riser there is a corrosion resistant layer of 3 millimeter which is going to handle the scouring effects of the carbon dioxide. Okay. You see here, along the inner side, there is going to be 3 millimeter of corrosion resistance material, which is the duplex stainless steel, which is now going to handle the corrosion problems, right. So, that is what we are planning now. So, furthermore, a stainless steel substrate is used to deposit the material during VAM. Now, we are looking at the manufacturing process. Okay. The power source used for deposition is Fronius cold metal transfer, which is CMT, Transpulse Synergic 4000. A welding torch is used for depositing materials. In layers. The whole process is now controlled using triaxial computer numeric control machine which we call as CNC, which I am going to show the photograph here. So, you have the CMT torch, you have the substrate, and you have the 3-axis triaxial CNC machine, which is now going to be used to manufacture or fabricate this FGM. Of course, the whole process is also measured and monitored using an high speed camera and also an oscilloscope for varying the pressure and also measuring the response of the wire feed or the rate of wire feed with respect to the manufacturing process. Okay. So, G codes are used. G codes are programmed to drive the metal deposit along X, Y, Z axis So, a typical G code which is used for a bidirectional strategy is shown here. So, this is the bidirectional weaving pattern for successive depositions. And this figure shows the scan weaving path of metal deposit. Okay. So, one can say this scan pattern, what you see here is being mapped here, and that is the substrate which is actually stainless steel. Below that there is a base, and CMT torch and electrode wire are being fed, and the wire is fed in the same pattern which is actually obtained depending upon what is the wire feed rate and how the pattern will be established to get a normal thickness of the desired value. Okay. Having shown this, the functionally graded material now is manufactured, or I should say is built in two stages. So, essentially we must realize that this FGM contains two materials. One is carbon manganese steel, other is duplex stainless steel. The thickness, shape, everything is fixed. So, they are fed in wires in the form of wire, and we are going to deposit it in two stages. So, to bind these two, we also require a filler material. The filler material is actually used in this case is ER70S6, which is compatible with carbon manganese steel and ER2209 grade, which is a duplex stainless steel. Okay. So, now we can show the chemical composition of the filler material. The chemical composition of the filler material is shown percentage by weight. Okay. It has got carbon. So, ER70S6 and ER2209. In fact, there are two filler materials. Okay. I am giving the value of both the filler material being used in our research. So, about 0.06, here it is 0.008. We have also used manganese, the content which has got 1.45, this contains 1.62, silicon 0.9 and 0.49, phosphor 0.02 and 0.016, sulfur 0.03 and less than about 0.005, 0005, very negligible. It contains nickel of 0.12, 8.59, very high content. Okay. It contains chromium of 0.12 and this contains 22.93. It has copper of 0.4 and this contains 0.083. It also has nitrogen, which is very insignificant, whereas in this case it is 0.152. It also has vanadium, cobalt and ferrum. Vanadium is 0.03, cobalt is negligible and ferrum is the balance. Whereas in this case vanadium is negligible, cobalt is 0.041, remaining is the balance. So, we have got the chemical composition of two different filler material which has been tried in this current research to fabricate the functionally graded material constituting two ingredients, duplex stainless steel and carbon manganese steel. Okay. The arc energy being used for manufacturing or otherwise the heat input required per unit length of the wire in the deposition process is given by this equation, which is IP, the heat input, which is 1 by n of summation of I equals 1 to n, UI and II, where UI is the instantaneous voltage and II is the instantaneous current. Okay. Arc energy is therefore given by the efficiency multiplied by the input, heat input, divided by nu. Usually the efficiency of VAM, wire deposition process, is taken as 80%, and the variable parameter in this case is going to be the nu, which is called as the deposition speed. The deposition speed depends upon the wire feed rate and also depends on the ingredients of the metal. Okay. So, the deposition parameters are then optimized, and these are the following data being used in the current study. So, the deposition parameters for FGM composition. These are the welding parameters for duplex stainless steel and for carbon manganese steel. The welding process being used is CMT in both cases. The filler material being used is ER2209, and in this case it is ER70S6. The filler diameter which is used for fabrication is 1.2 millimeter in both the cases. The mean current being used for depositing is 119 amperes, whereas in this case 107 amperes, and the mean voltage developed during the deposition process is 12.86 volts, whereas in this case 16 volts. The shielding gas being used is the pure argon gas in both the cases. The gas flow rate being used is 16 liters per minute in both the cases. Okay. The arc energy developed is in this case 222.59 kilojoules per meter, whereas in this case it is 256.8 kilojoules per meter. The welding speed of the torch is 330 millimeters per minute for fabrication, whereas in this case it is 320 millimeters per minute. So, these are the deposition parameters which is being used in fabricating this FGM. So, friends, we have learnt in this lecture more details about the FGM process, the ingredients of the experimental FGM we did, the properties of the constituent metals and weld parameters. So, in the next lecture we will discuss more in detail about the welding process, fabrication of FGM and the mechanical and structural properties of the fabricated FGM and compare it with the parent metals and see how they have improved when FGM is formulated. Thank you very much. Have a good day.